Hello everyone, welcome back. It's a little bit of a different video today. We're going over Navier Stokes assumptions and what terms they cancel. So, the reasoning for this video is because I wanted to try something new. And also, I felt like there weren't that many videos online that cover this topic already. So I figured why not make a video and we'll see how it goes. Hi, so real quick. You're talking to my Minecraft character right now because it felt a bit weird just to leave you on a blank screen, but I want to give a quick disclaimer. I myself am a university student, so please take everything in this video with a huge grain of salt. Everything you see in this video are things that I've learned in class or through examples or just noticing like different patterns from different examples. So again, watch knowing that maybe some of this might be slightly wrong because it is coming from a university student. Alright, thank you. So before we get started with the assumptions, this right here, this like 20 term equation is the full Navier Stokes equation. And as you can see, there's a lot of terms. In fact, the full Navier Stokes equation, while theoretically possible, has not been solved. So that's the reason why we have to make assumptions so we can cut down some of these terms to make the equation more manageable. So with each Navier Stokes problem, it's good practice to go ahead and start with the full Navier Stokes equation. So all 20, 25, 30 terms, however many there are that you see on screen here. And it's also good to start with the continuity equation, and you'll see this come into play in one of the later assumptions in the video. Okay, we're gonna go ahead and start with some of the simpler assumptions, starting with incompressible flow. This just means that the continuity equation is equal to 0. That is, these terms right here all cancel out. In fact, the incompressible assumption is actually a pretty common assumption that we're gonna go ahead and assume incompressibility for the rest of the video. So for future assumptions, you'll see that the Navier Stokes equation already has these terms canceled out. Okay, next assumption is steady flow. This one just means that the flow does not change over time. So that is anything with dt is equal to 0. That is these terms right here. They all get canceled out. Next, no pressure gradients. So this one means that any pressure term goes to 0. And this is anything with a p in it, anything that is pressure related goes to 0. Make sure that you get your p's and rho's straightened out because there's rho's, which means density, and there's p, which is pressure. Just make sure you know which one is which. In this case, it's these three down in the middle, and they all get canceled out. Finally, for the last simpler assumption, we have no body forces. This just means gravity is not there. All gravity terms are 0, and this would just be the last column. They all get canceled out. Just a quick note. If there are body forces, most of the time it's usually only the gy that survives as gravity acts downwards. The only time that multiple gravity terms survive is, for example, if we have like an inclined slope with fluid flowing down, then you would have gravity components going each way if you set your coordinate system along the slope and perpendicular to the slope. Okay, so now we're getting into some bigger assumptions, starting with unidirectional flow. This means flow is in only one direction. So if, for example, if we say flow in only the x direction, this would mean that all v and w terms are equal to 0, which means anything with a v or a w in the Navier Stokes equation gets canceled out. So as you can see, it cancels out a bunch of terms, but these aren't all of the terms. Remember when I said it's good practice to start with the full Navier Stokes equation and the continuity equation? Well, this is one of the assumptions that the continuity equation comes into play. So here, I have the continuity equation right here, and remember, it has the incompressible flow assumption attached with it, and that's why it's equal to 0. But if we go ahead and cancel out these two terms here, because of our example where we said flow only in x, we would have v equal to 0 and w equal to 0, so the latter two terms get canceled out, just leaving us with du dx equals 0, which also means that the second derivative of this also is equal to 0. So these are two extra terms that we can cancel from our Navier Stokes equation. If we go ahead and go back to we can see that these two terms here they get canceled out because of the continuity equation, and I marked them in blue just so you guys know that this is from the continuity equation. Next, we have 1D flow. Okay, before we get into 1D flow, I just want to make one thing clear. Unidirectional flow and 1D flow are not the same thing, even though they might sound similar. The main difference is that unidirectional flow only tells you that your fluid is going in one direction, so it only has one velocity component, while 1D flow also tells you that, but it also tells you that your fluid is not changing in any other direction. In other words, unidirectional flow can be thought of U in terms of X, Y, and Z, while 1D flow is just U in terms of only X. So 1D flow is a stronger assumption than unidirectional flow, as it will cancel more terms, 2 extra terms to be specific. Okay, so 1D flow is flow and change in only one direction. So for example, if we do 1D flow in the X direction, we will get V equals 0, W equal to 0, and we'll also get 2 extra terms, du dy and du dz equals to 0. Also, I have the continuity equation on the upper right. The same explanation that I did earlier with unidirectional flow also applies to 1D flow. So you can see here, all these terms cancel, and the blue ones are because of the continuity equation up on the upper right. The next two assumptions are very similar to our previous two. We have no flow in a direction, or you could say flow in two directions. Like I said, this is very similar to unidirectional flow, but now we just have flow in two directions instead of only one. So, for example, if we say there's no flow in the z direction, that would mean W is equal to 0. So all these terms here go to 0. And the continuity equation doesn't come into play for this assumption. Next, we have 2D flow, and similarly to 1D flow and unidirectional flow, flow in two directions in 2D flow are not the same. As you can see here, if we go ahead and do an example of, let's say, 2D flow in X and Y, that means W is equal to 0, and two additional terms, dv dz and du dz, are also equal to 0. So two extra terms are canceled when compared to the previous assumption. Okay, and finally, I just wanted to leave a little comment about laminar flow at the end. Laminar flow assumption itself doesn't actually cancel any terms in the Navier Stokes equations, but it does tell you that the flow is not turbulent, which basically means that laminar flow allows you to assume 1D or 2D flow. So basically, the 1D and 2D flow assumptions are only really possible if you have laminar flow. Okay, that was the last assumption that I had on this list. I hope you guys enjoyed this video. So again, just to reiterate the disclaimer from earlier, I am currently a university student myself, so please take everything that was presented today in this video with a huge grain of salt. Just know that it is possible that some of this information is incorrect. Alright, I hope you found this video helpful. If so, that's awesome, and I hope you have a good rest of your day.